This is Jack Jackson. In this video we're going to talk about some geometric visualizations of some examples of the power rule and also some applications of the constant multiple rule. So let's start by backing up here a little bit and look at some contextual applications right here or at least one contextual application of the constant multiple rule. So here's the question we want to look at. Joan is a sales manager for a sales team, and she earns 5% of the revenue from the sales of members on her team. Now, Frank is a salesman on her team, and Frank's sales have been increasing at a rate of $5,000 per year. How do Frank's sales affect the increase or decrease in Joan's income? Well, Joan's income, the part of it at least that's based on Frank's sales, okay, is given as J of t, which is just 0.05 times F of t, where t is time and F is Frank's sales. So by the constant multiple rule, J prime of t is 0.05 times F prime of t. Well, F prime of t is the rate of change in Frank's sales, which is $5,000 per year, and she gets 5% of that, or $250 a year increase. So due to Frank's increased sales, Joan's income is increasing by $250 per year. And so there's an example of a real world example of how the constant multiple rule works. I want to look at a couple of real world examples of some power functions now. And so by the power rule we know that if f of x equals x squared, then f prime of x is 2x. Now let's think about what this means. If we look at this picture here, we can see that what we have, by the way, what do we call it when we raise something to the second power? Well, we call it squaring the number. Why do we call it squaring a number? Well, that's because it's actually an area of a square. So if this side running along here is side x, and this is x, of course x here and x here, so this is a square with all sides being of length x, its area is x squared, x to the second power, x squared. Now, if we increase the size of this by increasing x, look what's happening here. We're adding some little delta x or h to this side here and this side here. Well, that makes a bigger square, and the side of the big square is just x plus h. So the whole area of the big square is x plus h quantity squared. Well, if we apply the distributive property to that, or FOIL, and we come up with four different parts. We get x squared here for the first. The outer and inner products are both x times h, and the last times last is the h squared. And so we see that we have these four areas. Now when we subtract x squared, the big square here that's in tan cancels out. So the amount of growth is given by this blue part here and here, and the red part in the corner. The rate of change in the growth is when you divide by h, so these h's cancel out, and this blue part and this blue part basically just becomes the length x here and here. This h squared cancels out and becomes h. As we take the limit as h goes to 0, this red part in the corner basically disappears, and what are we left with? We're left with the x here plus the x here is 2x. And of course that is the derivative. So how can we visualize the derivative of x squared is 2x? It's because this is growing on two sides, that this side and this side are both x. Okay? Let's look at a similar example. Let's say we take a circle. Okay? And we look at what's happening with a circle. Okay? Look at the picture here. Well, if you look at this picture here on the circle, what's happening is we have a circle here, radius r, and of course its area is pi r squared. Its circumference is 2 pi times the radius, or pi times the diameter. And then if we add something to the radius, we're adding this h here, or delta x, or adding it to the, or delta r, I guess we should say, adding it to the radius. Well, then we get the area of this new circle here. The amount of growth is this lighter purple ring here. We call that an annulus of a circle. It's just the area of a circle minus a circle inside. And its area turns out to be the circumference 2 pi r for some radius that's halfway between the radius of the inner circle and outer circle. But if we take the limit as h goes to 0, that basically just approaches the r there, and so we get 2 pi for that. Well, what's the derivative of this? So dA over dr is 2 pi r. And of course, that's the same as the formula for the circumference of a circle. That's no coincidence there. Where is it growing? It's growing all around the circumference. Okay, let's try another one. Let's try a volume now. Of course, just like we call raising the second power squaring, we call raising to the third power cubing. Okay, why? Well, take a look at the picture here. It's the volume of a cube. Okay, let's see if you can see it here in this picture. This is supposed to represent a three-dimensional object. So here we have x vertically from here to here, x across from here to here, and then x from here to back here to this point, to this first red dot here from this one in the corner. And so if we go that far and we make a box, a rectangular cube out of that, it's x by x by x, or x to the third power, is the volume of that. Now, when we expand x, where is it growing? Well, it's growing, each side is growing. So this is growing by delta x, or h here, and the back is growing by h, going out the back. So it's going out the back here, h as well. Well, what does that give us? So that gives us a flat part right here, little box that you can see kind of in blue, that it's growing. Its width is delta x, which is h, and this is an x by x, or x square is the area, times the h here for volume. This, we get the same size shape on the top and one on the back as well. Can you kind of see that? Okay. And then we have we do have some little pieces here. There's a little piece right here, three little pieces here that are h by x, and this one in the end that's h cubed. And if you remember when we did a proof of this and we expanded x plus h out to the third power, what did we get? We got x cubed. We got plus 3x squares times h's, 3x square h's. We got 3, these little things, so that's 3 squares with the thin delta x width. And then we got those are on the back side and the top. Then along the edges here, and the back, across the top, we got these little things that are x long and h by h on the end. So that's h square x. There's 3 of those, and there's 1 h cubed in the corner. It's exactly what we get. Well, when we subtract the x cubed, the big cube goes away. And so the amount that's changing is all this other part. Well, if we divide by h, then each of these things at the top, the bottom, the side, and the back are all basically just the area h, x squared by h, but to divide the h out to get a rate of change, that's just x squared. So each of these is x squared. There are 3 of those. And when we take the limit of h goes to 0, this other part here around the edges in the back goes to 0. So what's left? Where is the cube growing? It's growing on 3 faces. Each of one of those faces has area x cubed. So that's why the derivative, there's all the things there. Okay, so it's why the derivative is 3x squared, and that does go by the power rule. So you can kind of see in some of these cases, you can visually see why the power rule turns out to be what it actually is.